In current electricity, now we study Faraday's laws. In this class, let us confine to what is induction, how it is explained by Faraday, what is magnetic flux, what is the measurement of magnetic flux, what is Lenz's law, how it is explained, and then Faraday's electromagnetic. Faraday's experiment. Insulated copper wire is wound on a wooden rod has two coils P and Q. P and Q are two coils of copper wire which are wound on a wooden rod. The ends of the coil P are connected to a battery through a tap key. The ends of P are connected to the battery and the ends of Q are connected to a galvanometer. We notice a deflection in the galvanometer when the circuit is closed or open. When the tap key is pressed and the circuit is closed, we notice deflection. When the tap key is open, that is, we notice deflection in the galvanometer. So whenever the circuit of P is closed or open, a current is shown in the galvanometer. There will be no deflection in the galvanometer as long as the current is constant. If the current is constant, there will be no deflection in the galvanometer. We notice deflection only during the make and break of circuit in P. Because of the current in P, a current is induced in the second coil Q. This current is known as induced current. The EMF responsible for this current is known as induced EMF, and this phenomenon is known as induction. Induced current in a coil due to the motion of a magnet or a coil. Let us consider a coil of wire kept horizontally. A coil of wire kept horizontally with its axis on a horizontal line. Keep a magnet with the axis of the magnet coinciding with that of the coil. Keep a magnet so that its north pole is towards the coil and its axis is coinciding with the axis of the coil. We notice deflection in the galvanometer whether we move the magnet towards the coil or away from the coil. The upper figure shows the magnet moving towards the coil. In that case, if the deflection is to the left, then the lower figure shows the magnet moving away from the coil. In this case, the deflection will be to the right. So the deflection will be opposite. When the magnet is moved towards the coil, if the deflection is to the left, then the deflection will be to the right when the magnet is moved away from the coil. Notice that the north pole is facing towards the coil in both cases. This deflection will be noticed. This deflection in the galvanometer will be noticed. 1. When the magnet is moved towards the coil or away from the coil. 2. The coil is moved towards the magnet or away from the magnet by keeping the magnet constant or by moving both of them, both the magnet and the coil. And there will be no current when both are at rest. So, we notice deflections whenever there is a relative motion between the magnet and the coil. Just now we have seen a current created in the coil whenever the magnet is moved or the coil is moved. Now let us see the factors on which this current depends. The induced current depends on the following factors. One is the speed of motion of the magnet. If the speed of motion is increased, then the current will increase. Or if the speed of motion of the coil is increased, then also the current will increase. We also notice an increase in current if we use an iron core inside the coil instead of a wooden core. When the wooden core is there, the current will be less. If an iron core is placed instead of wooden core, the current will be more. So it depends on the medium in which the coil is situated. It also depends on the number of turns of the coil. The current increases with the increase in number of turns. We notice that a magnetic field is created at the position of the coil, and this magnetic field is changing as the coil is moved or the magnet is moved. So there is a change in magnetic field that is linked with the coil, and we notice the current is produced whenever there is change in magnetic field. So changing magnetic field related with the coil is studied with a new concept known as magnetic flux. In fact, if you change the orientation of the coil, then also the current changes. Hence, we study this phenomenon with a new concept defined and named as magnetic flux. We also know that a magnetic field is produced whenever a current flows through a coil. We have studied it already. Magnetic flux. Magnetic flux. To understand magnetic flux, let us consider a magnetic field B situated horizontally. In the magnetic field, a circular coil is situated, and the normal to this circular coil is to be considered here n bar, and in the first case it is making an angle theta. The normal of the coil is making an angle theta with the direction of B. To have greater understanding of this normal, let us imagine that the coil is in the plane of the screen. The coil is in the plane of the screen, then the normal will be out of the screen or into the screen. That is indicated by dotted n bar. Dotted vector n bar indicates the normal. It is out of the screen. If the coil is perpendicular to the plane of the screen, then the normal will be in the plane of the screen. It is indicated by solid vector n bar. Now, this is only to give the understanding of the normal situated with the circular coil. Let us imagine that the coil is placed at an angle theta. The normal is making an angle theta with the direction of magnetic field. Then we are concerned only with the components of the lines normal to the plane of the coil. We are concerned with the lines, magnetic field lines, components of these lines normal to the coil, that is known as magnetic flux. Now let us define flux. If A is the area of the coil and n bar is unit vector along the normal and B bar is magnetic field induction vector, then the flux is defined as phi is equal to A n bar dot B bar. That is, the dot product of the area vector and magnetic field vector gives the flux, magnetic flux. The magnetic flux is given by the dot product of area vector and magnetic field vector, A n bar dot B bar. That is equal to AB cos theta, because we know that dot product is given by cos theta. So phi is equal to AB cos theta. Instead of a single coil, if the number of turns of the coil is say n, then the flux linked with the n coils is given by phi is equal to NAB cos theta. N indicates the number of turns. So the flux phi, it depends on NAB theta. So phi increases with the increase in N, A or B. That is number of turns. If there is increase in number of turns, flux will increase. If there is increase in area of the coil, then the flux will increase, or the flux will increase with the increase in magnetic field induction. But the flux will decrease with the increase in angle theta. If theta increases, the flux phi will decrease. Lenz's law. Lenz's law gives the direction of induced EMF. It states that the induced EMF always tends to oppose the change in magnetic flux, that creates this current. The induced EMF always tends to oppose the change in magnetic flux which creates the EMF. That is the statement of Lenz's law. Now let us try to understand this law. Let us take a circular coil and a magnet. The magnet is placed towards the coil, the north pole of the magnet facing towards the coil, and suppose this magnet is moved towards the coil. Then a current flows in the anti-clockwise direction in that phase. An anti-clockwise current flow in a coil creates a north pole. An anti-clockwise current flow in a coil produces north pole. Hence, the north pole due to the induced current opposes the north pole of the magnet which is coming towards the coil. Instead of north pole, if the south pole is faced towards the coil and the magnet is moved towards the coil, then the current flow will be in the clockwise direction. The current flow will be in the clockwise direction because the clockwise current flow produces a south pole and opposes the motion of the magnet. So, when the magnet is moved towards the coil with its north pole towards the coil, anti-clockwise current flow takes place and a north pole will be created. If the magnet is moved towards the coil with its south pole facing towards the coil, then a clockwise current flow takes place in the coil and thereby a south pole is created in the coil. In both the cases, it will oppose the motion of the magnet. Let us try to analyze Lenz's law, interpretation of Lenz's law. When we consider the motion of the magnet towards the coil with its north pole facing towards the coil, the magnetic field at the site of this coil will be increasing. The magnetic field is, say, towards the right and this magnitude will be increasing. So, the current created in the coil should try to decrease this magnetic field. So, it creates a magnetic field in the opposite direction. So, the net magnetic field will be reduced, decreased. So, whenever the magnet is moved towards the coil, say from left to right, and the magnetic with the north pole towards the coil, then the magnetic field is to the right. Due to the flow of the current in the anti-clockwise direction, the magnetic field will be from right to left. It opposes the magnetic field created by the coil. It opposes the magnetic field formed by the magnet because this magnetic field will be increasing. Here, the cause of the induced current is the increase in magnetic field. The cause of the current is induced current is increase in magnetic field. So the current which is produced, induced current, it tries to decrease the cause. So it tries to decrease the magnetic field, which creates this current. Let us take the other case. Suppose the magnet is moved, withdrawn from the coil. The magnetic field associated with the coil, the magnitude of the magnetic field decreases. Though the direction is from left to right, the magnitude of this magnetic field decreases. So, a magnetic field will be created by the current flow, induced current in the same direction, so that the total magnetic field increases. Because here the cause is decreasing magnetic field. The induced current is created here due to the decrease in magnetic field. Hence, the induced current tries to increase this magnetic field. So, a magnetic field will be created in the same direction due to the induced current. If there is no opposition, if the induced current do not oppose the cause, then by a small motion given to the magnet, the induced current will attract this magnet and thereby no work need be done to move the magnet to produce the induced current. So, it automatically creates. So, automatically energy will be generated. This is against the principle of conservation of energy. So, Lenz's law says that this electromagnetic effect will also obey conservation of energy. Here, when the work is done in moving the magnet, it will be it is used in moving the charges, and thereby heat is generated. So the work done ultimately ends up in the form of heat energy. Now let us pass on to Faraday's law of induction. Whenever the magnetic flux linked with the electric circuit is altered, then an EMF is induced in the circuit. Whenever the magnetic flux linked with a coil changes, then an EMF will be induced in the circuit. This is Faraday's law. Let d phi be the change in magnetic flux in a time dt. Then d phi by dt is known as rate of change of magnetic flux. According to Faraday's law, this rate of change of magnetic flux is equal to the induced EMF. This is Faraday's law. E is equal to d phi by dt. D phi is change in flux and dt is the time in which the change in flux takes place. So E is equal to induced EMF E is equal to d phi by dt. This is mathematical form of Faraday's law. Now let us introduce a negative sign. E is equal to minus d phi by dt. This negative sign is induced to incorporate Lenz's law. According to Lenz's law, the induced EMF opposes the cause. So I am introducing a negative sign to incorporate Lenz's law into Faraday's law. This is mathematical form of the induced EMF by combining Faraday's law and Lenz's law. Then phi, the phi is flux, magnetic flux. This flux depends on the number of turns. If phi is the magnetic flux due to one coil, then due to n turns of the coil, due to one turn the flux is phi, due to n turns it is n phi. So relation becomes E is equal to minus d by dt of n phi, minus d by dt of n phi if the coil contains n turns. If the coil is placed with its plane perpendicular to the magnetic field, then the angle between the magnetic field vector and the area vector will be 0. So phi becomes equal to BA, where B is magnetic field induction and A is area of the coil. Hence the relation for induced EMF E is equal to minus d by dt of NBA. N indicates number of turns, B is magnetic field induction and A is area of the coil. This relation is valid only when the coil surface is perpendicular to the magnetic field, or the angle between the directions of the magnetic field and area vector is 0. The angle between them is 0. If a rod carrying current is placed in a magnetic field such that it forms a closed loop with a metallic frame, then the rod experiences a force. The force experienced by this rod can be indicated. It can be obtained from Fleming's right hand rule. In the figure, a magnetic field with crosses shows that the magnetic field is into the screen, and a U-shaped metallic frame is placed in the plane of the screen, so it is perpendicular to the direction of magnetic field. A rod is placed on this U-shaped metallic frame so that it forms a closed loop. Then, if the current in the metallic frame is in the clockwise direction, the rod placed as shown in the figure, it experiences an upward force. Now, to find the direction of this force, we can use Fleming's right hand rule. Fleming's right hand rule says that stretch the forefinger, middle finger and the thumb of right hand in 3 mutually perpendicular directions. Thumb, forefinger and middle finger of right hand, let them be stretched in 3 mutually perpendicular directions. Now keep the forefinger in the direction of magnetic field. Forefinger in the direction of magnetic field, that is into the screen, and the middle finger in the direction of current, that is from right to left. In front of the screen, keep your right hand such that the forefinger is placed into the screen and the middle finger is to the left hand. Then the thumb indicates the upward direction. That indicates the direction of force. So whenever there is a force due to induced currents, then we can find the force due to these induced currents by Fleming's right hand rule. Summary of this class. Faraday noticed that a current flows in one coil due to the rise or fall of current in another coil placed nearby it. He also noticed a current flow in a coil due to the motion of a magnet along its axis moving towards it or away from it. To study this induced effect, he defined a quantity known as magnetic flux. We can calculate magnetic flux from the following relation: NAB cos theta. Here N is the number of turns. A coil of N turns with surface area A, if placed in a magnetic field such that the surface of this coil makes an angle theta with the direction of the magnetic field, then the flux is defined as NAB cos theta. Lenz's law states that the induced EMF will oppose the change in flux. d phi is change in flux and d phi by dt is rate of change of flux. The induced EMF is say E. Then E is equal to d phi by dt is the relation given by Faraday. Faraday noticed that the rate of change of flux is equal to E. But Lenz noticed that the induced EMF opposes the rate of change of flux. So we introduce negative sign.